In this video, we're going to go over the concept of Cross Program Invocations on Solana. This is when one program defines an instruction that internally invokes the instruction on another program. So when a user sends a transaction invoking the instruction on program A, when that instruction is processed, it also invokes the instruction on program B. You can think of writing Solana programs as simply defining a set of API endpoints that are hosted on the Solana network, where each instruction is an individual endpoint. And a cross-program invocation is simply defining an API that also internally invokes another API. Next, let's walk through an Anchor program that demonstrates how CPI works. So this program has two instructions, one called deposit and one called withdraw. We're simply going to deposit some SOL into an account owned by the program and then withdraw the SOL that we've deposited. So here in the first instruction, we can view the deposit here that defines the accounts required by the deposit instruction. We need a signer, so that's the user depositing funds. We have a user account that we're going to initialize if needed. That is a PDA, which we can see by the seed constraints. And we have some vault account that's going to be holding the SOL that we transfer, which is also a PDA. And then we need the system program because our deposit instruction is going to internally invoke the system program to perform the transfer. And this user account is a custom user account type that we define here that stores the following data. In the body of the deposit function, we try to get the user data. If it doesn't already exist, we initialize the data. And here is the cross program invocation. So we have our deposit instruction. Inside our business logic for our instruction, we're going to invoke the transfer instruction on the system program. And this is how it's done in an Anchor program. We define the accounts that the transfer instruction requires. So the from and to address, we specify the program we're invoking, which is the system program. We create what's called a CPI context, providing the program and accounts required by the instruction. And then we invoke the instruction, passing in the context and any additional parameters. So just like the context for our instruction allows our instruction to access the accounts for that instruction, the CPI context defines the program and accounts required for the instruction we're invoking. So what's happening here is when a user invokes the deposit instruction, our deposit instruction will invoke the transfer instruction on the system program to transfer LAMP ports from the user account, the vault account, which is a PDA. Next, we can inspect the withdraw instruction. We can first take a look at the accounts that the instruction requires. Again, we need the user who's going to be withdrawing funds. We have the user account, which is a PDA. We have the vault account, which is also a PDA that currently holds the deposited funds. And we still need the system program because for CPI, we're still invoking the system program to withdraw funds from the vault to the user. In the body of the withdraw instruction, we're going to first check that the vault has enough LAMP ports for the transfer. Then we're going to create a variable called signer seeds. These are simply the seeds used to derive the vault PDA. We have our optional seeds here and the bump seed. Then we perform the CPI just as before, where we define the instructions required by the transfer instruction. We specify the program we're invoking, the system program, and create the CPI context. Except in this case, we're transferring from the vault to the user. Since the vault is a PDA, it doesn't have a corresponding private key. However, we somehow need to sign for this vault in order to transfer funds from the vault to the user. One feature of PDAs on Solana is that the program from which the PDA is derived can sign on behalf of that PDA when performing CPIs by passing in the seeds used to derive that PDA address. And when we invoke the transfer instruction, the Solana runtime will derive the PDA using the seeds. If the PDA it derives matches an address in the CPI, in this case, it'll be the vault account, then that account is considered a signer for the duration of the CPI. So this is how our program can transfer funds out of the vault to another account, allowing the user to withdraw from the vault where the transfer is signed for by the program itself. And that's the basics of CPIs. Effectively, it's just an instruction that we define that internally invokes another instruction. And that if the instruction we're invoking in the CPI requires a PDA as a signer, the PDA can be signed for by the program by passing in the seeds used to derive the PDA. Here in the test file, we demonstrate how to invoke the instruction. We have all the setup up here. The instruction to invoke the deposit instruction is right here. So we call program.request, pass in the accounts required by the deposit instruction, pass in the arguments, and then send the transaction. We get back a transaction signature. Same with the withdraw instruction. We call program.request, pass in the accounts required by the withdraw instruction, pass in the arguments required, call send, get back a transaction signature, and we run the test. And we get the following output when we run the test. We deposit one SOL from the user to the vault, and we withdraw half of that SOL from the vault back to the user. So here we have an approximate equivalent of the Anchor program written using native Rust. We're not going to go over the whole thing, but the one thing I want to point out is that in a native program, We call this invoke sign function when we need to make a CPI with CPI signers, passing in these signer seeds here. And when we just need to make a regular CPI without PDA signers, we call this invoke function here. Under the hood, in the anchor program, this helper function does the exact same thing, where it still invokes the invoke sign function to call our transfer instruction. And lastly, we also have a Pinocchio program reference, where the Pinocchio crate has its own implementation for the system program with slightly different syntax to make a CPI. So here is how you make a CPI with signer seeds, and here is how you invoke the transfer instruction without signer seeds. So we have the anchor program, a native program, and a Pinocchio program for you to reference and link below.